Hello and a warm welcome back to my YouTube channel. This is how to address uncertainty and errors in IB chemistry. It's a simple approach. It was enough to get you top marks on analysis. If you put it into your exploration and keep it consistent in your method, you're looking at fantastic marks for your IA. So consider this an extension to how to ace your chemistry internal assessment 24 out of 24 video that I posted recently. Okay, let's begin. Errors come from three main sources. Equipment, these are the ones that you can write down. These are the ones that are wrote on the side of burettes and pipettes and thermometers and ammeters and all the other things that you can be using. Humans, that's you. These are the errors and limitations of and subjectivity of our senses. Not that we made a mistake. This is a common misunderstanding. It's not I dropped something. It's not I failed to do something. It's not I forgot to measure something. It is, little TOK moment here for you, the limitation of your senses on the ability to monitor a reaction. We've just been doing the old disappearing cross with my chemistry group and given the same experiment and different eyes on that experiment, each student will decide a different amount of time for that reaction to complete, depending how good, bad, or indifferent their eyesight is. Same experiment, same beaker, same chemicals made by the same technician, but different results. These are human errors. You should make note of those also. Your method will be wonderful and bulletproof and fantastic, won't it? I'm sure. Your method is where your systematic errors come from, more of that in a moment, and your equipment is where your random errors come from, which you can write down. Okay, we don't want to end up like this unhappy scientist here, so how do we prevent that? We make a good method. So for every measurement that you take, there will be an error associated with it, whether it is equipment related, human related, or method related. Systematic errors, those are the errors which are due to either calibration or consistently poorly cleaned material. We'll come to more of those things in a moment. These will affect the accuracy of your measurements, which I'm about to go through in a second, as you just saw. So systematic errors, you cannot remove these by doing repeats. Repeats will not remove systematic errors. Repeats will remove random errors, or they will reduce. It's better. Repeats reduce. I love the alliteration of that. Random errors. So the more repeats you do, at least in triplicates over your 5 independent variable data points, the greater your precision will be. So it's important to know, just to recap, equipment, random, humans, you, and anybody else, not that you're an idiot, that you are limited as a human being, TOK, and the method, those are your systematic errors. Okay, systematic affects the accuracy, and random affects the precision. Got that clear? Let's move on. So I've clipped this slide from Lawrence Koch. I've credited that underneath. The link is there to the full presentation. I suggest you go and look at it and all his other presentations. Fantastic presentation. Must have taken him years to make them. I'm glad he has the patience. So let's borrow that. Thank you, Lawrence, for this clip. So measurement, there are 3 types. There's precise and not accurate. There's precise and accurate, and precise and not accurate. I used to teach this in the UK, and when I did that, we used to talk about the accuracy of shooters during the any of the world wars. You choose it. So in the First World War, there were just machine guns that spread bullets everywhere, and the bullets went all over the place, and now and again one might hit a target. They were neither precise nor accurate. Neither precise nor accurate. As time went on, a bit later on during the war, they became more precise. They were able to hit the same spot. So if you were sat on a wall firing at the enemy, you could pretty much hit the same spot. That was great, but it didn't hit the right spot because the enemy was still firing back at you. Okay, by the end of the war, precise and accurate, maximum damage was caused because the groups of bullets were grouped together, which is precision. Precision is grouped together in the same spot. and accurate. And accurate is at the true value, which for chemistry purposes, then accurate is close to the literature value, which is the true value. I always think accurate and true kind of sticks together in my head. If that works for you, use it. If not, don't worry about it. Okay, so we can have precise, not accurate, precise and accurate, and precise and not accurate. The two types of errors, we've got systematic and random errors. Systematic, they affect accuracy, mentioned that on the previous piece of paper, and random affects the precision. Okay, this one has high random error. They are all over the place. This one, so this is neither accurate nor precise, it's this situation here. So those two are the same. This one has high systematic error. They're grouped together, but they differ from the literature or true value by the same amount consistently. Okay, so random errors, what can we have? Instrument is imprecise. All instrumentation is imprecise. All instrumentation has an uncertainty. The most expensive, wonderful piece of kit in the world to measure will still have an uncertainty. It's probably so expensive because we know that in uncertainty with a great deal of accuracy. Okay. This can be a burette reading or pipette, small sample size, not enough trials. You shouldn't be guilty of that if you're filling your 10 hours for your IA. And any statistical fluctuations of measurements. Okay, so the unpredictability inherent in most chemistry experiments, which I'm sure you will have seen as you've journeyed through your IB. Okay, for systematic, instrumentation not calibrated, I'll put that at number 1 as well. Check on the back of your balances, your decimal place balances in your school laboratory. There should be a sticker with the last time it was calibrated. And a person will come around with calibrated masses, which also have their own uncertainty, and then they will calibrate that balance against those masses once every year, because every time it's used, I know you're wonderful Year 11, Year 12, Grade 12 students, and you treat your balances with great care and respect. But cast your mind back to being in Year 9, and when you pressed as hard as you could on the balance lid to see what happened to the display, and of course it said error, then they do go out of tolerance quite quickly in a school laboratory setting. Faulty apparatus, this happens as well. Data loggers break, colorimeters break down, ammeters get tired, imperfect, incorrect measurement, and the procedure or the method was incorrect. So you introduced a systematic error by virtue of your design. Hard to spot, but if we spot it, that's great things to talk about in your evaluation. So obviously the ideal is we want to both be precise and accurate. The question is, in a high school laboratory, to what extent can you do that? Don't forget, the most accurate thing that you're going to perhaps use, let's put a tap there, forgive my terrible drawing, is a burette. Most burettes have a range of 0 centimeters cubed to 50 centimeters cubed, and printed on the stem, normally up here, there is an uncertainty if it's expensive. If not, it's half the smallest division, so it's plus or minus 0.05 cm cubed, and that's an ideal way, if you're saying what a burette is, to write it down. But don't forget, these burettes are made of glass, and they're made of glass in a factory. And in that factory, they had metal casings or metal castings, and they, over time, will degrade over time. And a burette is only accurate to this level of certainty at a certain temperature, normally at 20 degrees C. Obviously, as things get hotter, they expand, so it's no longer 50 centimeters cubed. I saw a student the other day using one of those cheap plastic pipettes to dispense an accurate amount of liquid that we're going to use in a calculation. And there are 2 marks on it. One is 1 cm cubed, one is 2 cm cubed. And they were using this to accurately measure, or claim to measure, 2.0 cm cubed with an uncertainty of plus or minus 0.01 cm cubed. That clearly is incorrect. These are mass-produced by the million. They're also made of plastic, so they're terrible for the environment. They're not made to any level of precision or accuracy whatsoever. For transferring a starch indicator or indigo carmine or whatever it is you're using, they're absolutely fine. For accurate measure, these are less than 1 cent a piece. There is no way you can use one of these. So whenever you're doing your IA, always use the most accurate or precise piece of kit that you have. So accuracy and precision. Random errors can be reduced by repeats. Systematic errors cannot be. We need to talk about random and systematic in our evaluation if we are going to get full marks. Okay, so we can propagate absolute or relative uncertainties. I'm going to explore what those mean now. Okay, so absolute is just pretty much just the number, the numerical value, and it can be found by adding them together. So an absolute uncertainty would be, I don't know, if we had a thermometer and it had 25.0 degrees C was the measurement, and for a thermometer it's plus or minus half the smallest division. The smallest division is 0.1 degrees C, so it's plus or minus 0.05 degrees C. Don't forget, if you do a T2 and a T1, if you're doing a delta T like you're doing a enthalpy calculation, then that also is plus or minus 0.05 degrees C. So for delta T, the absolute uncertainty is 0.1 C. These are fairly simple. Well, they're as simple as you can get them. You just add them together, like you have done here, to get the total. So then you quote, that was 25, so delta T in this case, with 25 degrees C, plus or minus 0.1 degrees C. Okay, you've tracked your uncertainty, but it's not very sophisticated. And it doesn't help me if I'm measuring a mass and a volume and a temperature change, or I don't know, the mass of an electrode, whatever it happens to be. We need to take these individual uncertainties and change them into relative uncertainties. Because when we have the percentages, then we can add them together to get the total. So individual uncertainty for each individual measurement you're going to use, which is used in a calculation, is the percent total uncertainty. For analog equipment, half of the smallest increments, okay? Unless it's printed, so always check. Get your I in there, that's an I, whatever the piece of kit is, and look, good kit will have the uncertainty printed on it. If it does, brilliant, use it. If not, half the smallest division, because that's where your eye can see. This is the human limit. Speak more about the human limit in a moment. Digital equipment is the last decimal place, but please use common sense. Okay, I could take a stopwatch and I could take the amount of time it takes me to make this video, and it might be, I don't know, 25 minutes, 38 seconds, 0.16 decimal points. Okay. This here is a big issue because there's no way a human being can react to work to that level of precision. For a human being, although the stopwatch will say 0.16 seconds, we take it back to 38. If it was beyond 0.5 here, 5, 6, then we take it to 39. So we always round the number. But there are no decimal places when we're talking about time. And that's not because the stopwatch is rubbish. It's not because we are. It's just a fact of life. We are not that precise. Give us an example then, Mr. Midgley. Okay. In a calorimeter experiment, the initial temperature was 10 degrees C, and the final temperature was 25.4 degrees C. The thermometer uncertainty is here, plus or minus 0.05. First thing I notice is that's the second decimal place. There's only one decimal place here. Given this uncertainty, the true value, the accurate value, the real value, like that, the real value, is minus 0.5 from the quoted here to plus 0.5. Okay, so the difference between the two of these is 15.4, so 25.4 and 10 is 15.4. So since it's 0.05, the reading is anywhere between 15.35 and 15.45. Okay, so the absolute uncertainty, you just add them together. 0.05 plus 0.05, 0.1, I couldn't find degrees on the Google Doc, degrees C. So the absolute uncertainty is 0.1 degrees C. So we could quote 15.4 degrees C plus or minus 0.1. So it's going to be somewhere between 15.3 and 15.5. Cool. Right. How do I work out the relative uncertainty? Well, we'll take the absolute uncertainty, divide it by the true value, which is there, times it by 100 to get a percent. Let's do that again. Take the absolute uncertainty, divide it by the value, the measured value, times it by 100 to get it in percent, and that gives me 0.6%. Now this is powerful. This is powerful because I can do that to every integer that I use during the generation of data to use in a calculation. Let's do something a bit more involved. In an experiment, a student measures the time it took for 50 cm cubed of a gas to be evolved at different temperatures. At 25 degrees C, it took 15.47 and the syringe was plus or minus 0.25 cm cubed. We can just assume that that was printed on the side of the syringe. Question is, what's the average rate and what is the relative uncertainty? Well, rate is volume over time, so let's work it out. 50 over 15 is 3.3. I prepared this before I recorded, obviously. The absolute uncertainty is given in the question. It's there, so just quote it. 0.25, and time uncertainty is always 1 second. If teachers are watching this, 0.5 I would accept as well if you're young, okay? Therefore, the relative uncertainties are absolute over the number times 100, so it's 0.5% of the volume. Time is 1 over 15, which is the difference, 15 times 100, which is 6.7. And the total uncertainty is then 0.5 plus 6.7 is 7.2. So just add them together, get the percent and add. So for addition and subtraction, it's always the sum of the individual uncertainty. If you're just adding or taking away something, the only way you do that, the only time you do that is when you're generating numbers for use later in a multiplication or division. This is the one that we're going to be using. For multiplication and division, you sum the percent uncertainty together, which I just did here. I just noticed there might be a small error there. It's 15, so it's 25 there. Let's say it started at 10 degrees C. So T1 was 10, therefore it's going to be 15 degrees C rise. But you get the idea. Uncertainty, value times 100%. Got it? Cool. So let's use it in a real experimental set of data. So 20 mils, I don't like that. If this was your IA, I'd be writing 20.00 cm cubed plus or minus 0.05 cm cubed. And then I go, yay, that's great. I don't like 1 m either, 1 mole per decimeter cubed. Maybe that's plus or minus 0.01 mole per decimeter cubed. Why did I not do that when I made the video? Because I wanted to do that for you now, okay? Excess calcium was added and final temperature T2, which I'll mention down below, was recorded. Calculate delta H. Well, we know delta H is MC delta T. Every man, woman, child, and beast knows this. So what do we have? Well, let's say the initial mass was 15 grams. Now it looks good, look. Same number, consistent decimal places. Common cause of marks down on analysis is inconsistent decimal places. 2dp, 2dp, beautiful. 2dp, 2dp. Fictitious numbers, but that's why they are there, so you can see the example. Initial mass was 15, final mass was 40, 2dp plus or minus 0.01. The absolute uncertainty, as we were doing previously, add them together, 0.02 g. The mass of the zinc sulfate, let's make some total, was 25 grams, 40 take away 25 here, plus or minus the absolute uncertainty, which is 0.02 grams. Very good, we're doing absolute. What about the temperature? 10.0, 0.2, consistent decimal places, tick. 56.0, 0.2, consistent decimal places, tick. The absolute is add them together, 0.4, so it's 46, the delta T, the change. 56.10, the difference is 46, plus or minus 0.4 degrees C. You with me? Excellent. Now let's make it useful, because we want to do MC delta T, we want to do this, don't we? So enthalpy, or Q in this case, Q is M2 minus M1, end mass minus start mass, times C, end temp minus initial temp. So let's plug the numbers in. So mass was 20, that's here, assuming a density of 1 gram per centimetre cubed. Specific heat capacity of water is 4.18, and 46 was the change in the temperature, which is there. So it's 3.8 kilojoules, or 3,800 joules. But this was in 0.02 moles. So if 0.02 moles are 3,800 joules, or 3.8 kilojoules, 1 mole is 3.8 times 1 over the 0.02. We need to scale it up. So it's 190 kilojoules per mole. So the percent uncertainty in the mass was 0.02 over 25 times 100. 0.02 over, here we go, over 25 times 100, 0.08. Temperature uncertainty is 0.4 here over 46, which was delta T, times 100, 0.87. T is the massive one. It's in 0.9, and it's almost going to be 1%. And when we do it together, it's around about 1% error. So take 1% of your 3,800, which is about 4 joules. The answer is 3,800 joules plus or minus 4 joules. So you see what we did? Get the absolute. Change to percentage, given the values. Add them together, and then take that percent of your final value, and that's the uncertainty in the same units that you are quoting in. Bingo. You got 6 out of 6 on analysis. I'll do graphs in a separate video, but I just wanted to give you a little gentle warm-up with this. I found this on a IB biology site, bless them. This is better than this. Yes, it is. But what's wrong with it? My gosh, where do I start? Title. Units. 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 Plus or minus, plus or minus, plus or minus, plus or minus. Error bars. Where are the error bars? Why is it not showing the trend? What's going on? There's a lot of things wrong with that. Excuse me. We'll do that in a separate video. I'll put this document below so you can look at the links. I've used these as the sources for this document. The university level treatment of uncertainty, that's this one here. So you can see if you're doing exponentials or natural logs or powers, this is what you have to do. But for IB, we do not. The absolute and the relative uncertainty will get you full marks. This was slide 2, which I clipped and used in here. All credit to Lawrence Cock, fantastic. Every presentation he does off the charts, brilliant. This gives you some exemplars to work through, more exemplars than I've given you, and work with significant figures and with decimal places. Andrew Weng, fantastic YouTuber, way more successful than I am, and some more worked examples here. So as a starter and as a way to actually get the marks for analysis, if you do this, you are well on the way to getting 6 out of 6. All from those first misunderstandings or understandings and not wishing to end up like this chap here. Okay, I hope you enjoyed today's video. Look forward to seeing you again. Please like, comment or subscribe at the bottom. Thank you very much for listening. Have a great day.